Welcome to Rational Classes. In this video, we'll dive into the fascinating world of 3D mensuration. We'll explore the formulas and techniques to calculate the surface area, lateral surface area, and volume of different 3D shapes like cubes, cylinders, cones, pyramids, prisms, and more. Whether you're preparing for a competitive exam or just looking to strengthen your basics, this video will make mensuration easy and interesting for you. So let's get started and unlock the secrets of 3D shapes together. Mensuration is a branch of mathematics that deals with the measurement of geometric figures, including their lengths, areas, volumes, and perimeters. It is broadly classified into two categories. Mensuration deals with the measurement of plane figures like squares, rectangles, triangles, circles, parallelograms, and trapeziums. 3D mensuration involves measurement of solid shapes like cubes, cuboids, cylinders, cones, frustum, spheres, and pyramids. Let us understand the meaning of some important terms used in three-dimensional mensuration. A flat or curved surface that forms part of the boundary of a solid object is known as a face. In the given example, the three visible faces of the cube are shown in different colors. Similarly, in another figure, the circular face of the cylinder is highlighted in red, while the curved face is shown in blue. The number of faces a figure has depends on its type. For example, a cube has 6 faces, whereas a cylinder has 3 faces, out of which 2 are circular and 1 is curved. A line segment where 2 faces or sides meet, forming the boundary of the shape, is called as edge. Black lines, including dotted 1, are the edges of the given respective figures. Corner points where 2 or more edges meet is known as vertex. Plural of vertex is known as vertices. Here, 8 figures are shown along with their number of faces, edges, and vertices. You can go through them to gain a clearer understanding. Now we will begin the first subtopic of our chapter, called lateral surface area. In this section, we will understand the meaning of lateral surface area and learn how to find it for different figures using visualization techniques. Let's get started. The lateral surface area, LSA, also known as curved surface area of a 3D geometric shape, is the total area of its vertical or curved surfaces, excluding the top and bottom surfaces. Let us understand with some examples. Area shown in the red color is the lateral surface area of the respective figure. Now we will derive lateral surface area of each and every 3-dimensional figure commonly used in mathematics. A cube is a 3-dimensional geometric shape having 6 square faces, all of equal size, 12 edges, and 8 vertices. We all know a cube have 6 equal faces, and each face have a square shape. Here we have to find lateral surface area of the given cube, therefore top and bottom will be discarded. Suppose this cube is open at the top and bottom. If we cut the cube vertically as shown in the figure and unfold it, we obtain a rectangle with a length of 4 and a breadth of a. The lateral surface area of the given cube is equal to the area of the rectangle formed. Thus, the lateral surface area of the cube is 4 square units. A cuboid is a 3-dimensional solid shape with 6 rectangular faces, where opposite faces are equal. A cuboid has 6 faces, 12 edges, and 8 vertices. A cuboid is defined by its length A, breadth B, and height h. Imagine you are sitting in your room where two opposite walls are painted red and the other two are painted blue. Since we are dealing with the lateral surface area, therefore we are not considering the roof and the floor. Imagine all the walls of the room are placed one after the other in a straight line. It will look as shown in the figure. Now, you will get a long wall with a total length of 2L plus 2B and a height of h. The total area of the four walls represents the lateral surface area of the room or the cuboid. Therefore, we can say that the LSA of a cuboid will be equal to the area of the four walls, which will be equal to 2L plus B into h. A cylinder is a three-dimensional geometric shape with two parallel circular bases and a curved lateral surface connecting them. It is one of the most common shapes found in everyday life, such as pipes, cans, and gas cylinders. In this figure, there is a hollow cylinder of radius r and height h, whose lateral surface area we are going to derive. Imagine this hollow cylinder is made up of paper. If you will cut it out vertically straight and open it, what figure will you get? Think over it by pausing the video. The lateral surface area of the given cylinder is equal to the area of the given rectangle. The height of the cylinder serves as the breadth of the rectangle, while the circumference of the circular base of the cylinder acts as the length of the rectangle. We all know that area of the rectangle is length into breadth. Therefore, lateral surface area of the cylinder comes out to be 2 times pi into r into h. A prism is a three-dimensional geometric shape that has two identical parallel bases and rectangular lateral faces connecting them. The cross-section of a prism remains the same along its length. Prisms are of many types, few of them are. Triangular prism, a prism with base as a triangle. Pentagonal prism, a prism with base as pentagon. Hexagonal prism, a prism with base as hexagon. If you go back in the video, you will notice one important thing, and that is, if a given figure has identical top and bottom faces with a parallel gap between them, then the lateral surface area is simply the perimeter of the base multiplied by the height through which the figure is extended. In short, lateral surface area of such figures is equal to perimeter of the base into height. For better clarity, we can observe in the given figures that their top and bottom faces are identical and are separated by a certain height. The lateral surface area of these figures can be determined by multiplying the perimeter of the base of each respective figure by its height. If you have understood this concept, then finding the lateral surface area of any similar figure, including prisms, will be as easy as a cup of tea for you. In the case of prisms, we can apply the same concept to derive the lateral surface area for each type. Accordingly, the lateral surface area of a triangular prism, as shown in the figure, is 3h. For a pentagonal prism, is 5. A hexagonal prism is 6h. Isn't it amazing to remember just one simple rule instead of memorizing multiple formulas? A pyramid is a three-dimensional geometric shape that consists of a polygonal base and triangular faces that converge at a single point called the apex. The number of triangular faces depends on the number of sides of the base. Pyramids are common in architecture, mathematics, and various real-world applications. They are of many types. 3 out of them are shown here. The slant height of a figure is the length of the slanted edge that connects the base to the topmost point, known as the apex. It is usually denoted by the letter L. The slant height is different from the vertical height, also known as altitude, which is the perpendicular distance from the base to the top. We can relate the slant height, L, the perpendicular height, h, and the base, r, or a side length, using the Pythagorean theorem as shown. To understand the lateral surface area of a pyramid, we will take the example of a square pyramid of side A, height h, and slant height L. In this figure, we are looking at one face of the prism where the base length is A and the height is L. It is important to note that the slant height of the given pyramid serves as the height for the triangular face of the pyramid. So the area of the given face of the pyramid comes out to be half into A into L. Here, 4 triangular faces of a square-based pyramid are shown. The combined area of these 4 faces represents the lateral surface area of the pyramid. As we can see, the area of each triangle is half multiplied by A into L. Therefore, by multiplying this result by 4, since there are 4 triangular faces, we obtain the lateral surface area of the pyramid, which comes out to be 2AL. To make it more easy, let us learn something more practical and easy to understand. The 4 blue triangles collectively represent the lateral surface area of a square-based pyramid. You can also see 3 large red triangles labeled as 1, 2, and 3. From the figure, it is clear that each large red triangle is a vertical flip of a blue triangle, which means that the area of a large red triangle is equal to the area of a blue triangle. Now, the 3 blue triangles match the 3 large red triangles in area. If the 4th blue triangle is cut into 2 equal parts vertically along the line L, the area of each part will be equal to the area of each smaller red triangle. The total area shown in blue is equal to the total area shown in red. The combined figure representing the total area of both the red and blue regions forms a rectangle with length 4A and breadth L. Therefore, the area of the rectangle becomes 4A, where 4 represents the perimeter of the square base of the pyramid. Since we need the area shown in blue only, which corresponds to the lateral surface area, it will be half of the total area of the rectangle. Therefore, we can say that it will be half of 4A, L, or half of perimeter of the base into height, L. So the final conclusion is that the lateral surface area of any regular pyramid is half the perimeter of the base into the slant height. A cone is a 3D figure having circular base and pointed vertex. There are 2 heights, one is perpendicular to the base, and the other is slanting. A cone have 2 faces. One is lateral and the other is circular. Slant height of the cone can be obtained by using Pythagoras' theorem as shown. To derive the formula for the lateral surface area of a cone, consider a cone with base radius r, height h, slant height L. Cut and unwrap the cone along its slant height as shown. The unwrapped shape will form a sector of a circle with arc length equal to 2 pi r, which is the circumference of the cone's base. Radius equal to L, which is the slant height of the cone. The area of a sector is half the product of the arc length and the radius r. In the sector, arc length is 2 pi r, and radius is L. Accordingly, area of given sector is equal to half of 2 pi r. Finally, we can say that lateral surface area of cone will be pi r L. Another way to understand this is, if a figure is pointed at the top and the top makes a perpendicular with the center of the base, as in the case of a cone or a pyramid, then the lateral surface area of such a figure will always be half the product of the perimeter of the base and the slant height. A frustum of a cone is the part of a cone that remains after slicing off the top portion with a plane parallel to its base. It has two circular bases, one larger and one smaller, a curved lateral surface, a height, h, a slant height, L. When the frustum is cut and open along the slant height, its curved surface unfolds into a frustum sector, also known as trapezoidal ring. To calculate the lateral surface area of the frustum, first we calculate the average circumference of the top and bottom part of the frustum. After this, we multiply this average circumference by the slant height of the frustum. Taking the average of the top and bottom circumferences accounts for the fact that the frustum's lateral surface is essentially a trapezoid. The average circumference gives the effective length of the shape when considering how it stretches from the smaller top to the larger bottom. Thus, the lateral surface area is effectively calculated using the average circumference multiplied by the slant height to reflect the tapering shape accurately. Our second subtopic in three-dimensional mensuration is total surface area of a figure. The total surface area, TSA, of a 3D figure is the sum of the areas of all its surfaces, both curved and flat. It represents the total amount of space covered by the outer surface of the solid. The area shown in the blue color represent the total surface area of the given respective figures. We have already learned about the lateral surface area of a 3D figure. Therefore, it becomes very easy to determine its total surface area. We simply need to add the areas of the top and bottom surfaces of the respective figure to the lateral surface area to obtain its total surface area. Here we have to find the total surface area of the given cube with side length A. Therefore, we will add the lateral surface area of the given cube to the area of top and bottom of the cube to obtain its TSA. We have already studied that lateral surface area of the cube is 4A square units. Top and bottom of the cube are of the same areas, that is, A square units. So by adding we get 6A square units. Here we need to find the total surface area, TSA, of the given cuboid with length L, breadth B, and height. To calculate this, we will add the lateral surface area of the cuboid to the areas of the top and bottom surfaces. We already know that the lateral surface area of a cuboid is twice the product of the sum of its length and breadth with its height. The top and bottom of the cuboid have equal areas, each being LB square units. Therefore, the total surface area becomes 2LB plus 2BH plus 2HL. Thus, the total surface area of the cuboid is twice the sum of LB, B, H, and HL square units. Here we need to find the total surface area, TSA, of the given prisms. Let the base side of each prism be N, the height B, H to calculate the TSA. we will add the lateral surface area of each prism to the areas of its top and bottom surfaces. We are going to derive the TSA of each prism separately. Here we need to find the total surface area, TSA, of the given prisms with base as equilateral triangle with side, A, and height, H. To calculate the TSA, we will add the lateral surface area of the given prism to the areas of its top and bottom surfaces. We had already learned that LSA of any prism is calculated by multiplying the perimeter of the base with its height. Perimeter of the base of the given prism is 3A and height is H. Therefore, LSA of the given prism will be 3A, H. Base and top surfaces of the given prism are in the form of equilateral triangle, whose area is given by square root of 3 divided by 4 into the square of the side of the triangle. Here the side of the triangular base is A. Accordingly, area of each top or bottom face of the given prism will be square root of 3 divided by 4 into the square of the side. Adding LSA with areas of top and bottom, we get the area of the given prism. Here, we need to find the total surface area, TSA, of the given prisms with base as a regular pentagon with side, A, and height. To calculate the TSA, we will add the lateral surface area of the given pentagonal prism to the areas of its top and bottom surfaces. We had already learned that total surface area of any prism is calculated by multiplying the perimeter of the base with its height. Perimeter of the base of the given prism is 5A, and height is H. Therefore, LSA of the given prism will be 5A, H. Base and top surfaces of the given prism are in the form of a regular pentagon whose area is given by the formula highlighted by yellow color. As the top and bottom faces are identical, therefore total area of top and bottom faces will be twice that is shown in yellow color. Adding lateral surface area with areas of top and bottom, we get the area of the given prism as shown. Here, we need to find the total surface area, TSA, of the given prism with a base in the form of a regular hexagon with side, A, and height, H. To calculate the TSA, we will add the lateral surface area of the given hexagonal prism to the areas of its top and bottom surfaces. We had already learned that total surface area of any prism is calculated by multiplying the perimeter with its height. Perimeter of the base of the given prism is 6A, and height is H. Therefore, LSA of the given prism will be 6A into H. The base and top surfaces of the given prism are in the form of a regular hexagon, whose area is equal to the area of 6 equal triangles, with sides equal to that of the hexagon. The area of each equilateral triangle is given by root 3 divided by 4 into the square of side, A. Since a regular hexagon comprises 6 equal equilateral triangles, the total area of the hexagonal base will be 3 times root 3 divided by 4 into side square. Since the top and bottom faces are identical, the total area of the top and bottom faces will be twice the area of one face. Finally, adding the lateral surface area with the areas of the top and bottom faces gives the total surface area of the given prism as shown. Here we need to find the total surface area, TSA, of the given cone with a base radius, r, height, h, and slant height, L. To calculate the TSA, we will add the lateral surface area of the given cone to the area of its bottom surface. We had already learned that total surface area of a cone is pi into r, into L. The base surface of the given cone is circular, whose area is equal to pi into r square. Finally, adding the lateral surface area with the area of the bottom face gives the total surface area of the given cone as shown. Here, we need to find the total surface area, TSA, of the given cylinder with a base radius, r, and height, h. To calculate the TSA, we will add the lateral surface area of the given cylinder to the area of its top and bottom surfaces. We had already learned that lateral surface area of a cylinder is 2 pi into r into h. The top and base surfaces of the given cylinder are circular, whose area is equal to pi into r square. Finally, adding the lateral surface area with the area of the top and bottom faces of the cylinder gives the total surface area of the given cylinder as shown. We had already learnt about different types of pyramids in the beginning of this video, as we know that total surface area of a figure is sum of its lateral surface area and the area it covers at the top and bottom faces. We had already derived the formulas for the lateral surface area of different types of pyramids. Therefore, to obtain the total surface area of the pyramid, we will just add the area of the base with its lateral surface area we had already derived. Students who had skipped the video may go back to learn the same. We had already learnt about the lateral surface area of a frustum in the first 20 minutes of this video, as we know that total surface area of a figure is sum of its lateral surface area and the area it covers at the top and bottom faces. Therefore, to obtain the total surface area of the frustum, we will just add the area of the base and the top with its lateral surface area we had already derived. Students who had skipped the video may go back to learn the same. A sphere is a perfectly round, three-dimensional geometric shape where all points on its surface are equidistant from a fixed point called the center. The distance from the center to any point on the surface is known as radius of the sphere and is denoted by the letter r. If we cut the sphere along its diameter, then the figure so obtained is called hemisphere. Have you ever wondered what happens when you open up a sphere? It might surprise you to know that a sphere can actually transform into a cylinder. Sounds impossible. Let's explore this fascinating geometric transformation. Now let's carefully open this sphere along its surface and stretch it out. What happens? Surprisingly, it forms a cylinder with a height equal to 2r, which is the diameter of the sphere. A circumference equal to 2 pi r, that is the length of the curved surface of the sphere. Now, lateral surface of the cylinder so formed is representing the surface area of the sphere. We already know that the lateral surface area of the cylinder is obtained by multiplying the perimeter of its base by its height. Accordingly, perimeter of the base is 2 pi r, and the height is 2r. Therefore, surface area of the sphere will be 4 pi r square. In this video, we have learned so much about three-dimensional figures. Hope you had enjoyed the learning. Before going further, I would like to say that if you like the video, then please don't forget to subscribe the channel, and I would be very happy if you also share this video with your friends. Let's start our final topic on three-dimensional mensuration known as volume. The volume of a three-dimensional figure is the amount of space it occupies. It measures the capacity of an object and is expressed in cubic units. Here, some three-dimensional figures are given. although all the figures are looking different from each other, but still, there is a similarity among them. The similarity is that the top and bottom faces of each of the figure are identical in itself. For example, a cylinder has identical top and bottom. If you want to find the volume of any of these figures or any other figure with such type, then I am going to tell you a single formula of finding volume for all of them. Volume of a figure is directly proportional to the area of the base and its height. As the area of the base and the top is same, therefore keeping it constant, volume of the figure will now depend on its height. Therefore, volume of such figures as shown will be equal to the area of base multiplied by its height. To explain this further, let's apply this concept to each of the given figures. In every figure, you can notice that the concept I have explained fits perfectly. For the remaining figures, you can try it on your own, and you will find that this concept works consistently. These are the second type of figures we encounter while studying mensuration. For such figures, I will provide you with a general formula for calculating the volume. The key point to remember is this: if a three-dimensional figure has a pointed top, apex, that aligns vertically with the center of its base, then the volume of the figure will always be 1/3 of the area of the base multiplied by the perpendicular height.